Hi, everyone. This is Harmonization Part 2, where we're going to be talking about machine learning and harmonization. So there's a lot of examples of machine learning in diffusionmri. For over a decade now, people have been trying to do disease risk prediction using diffusion measures. So this would be trying to predict, for example, early onset Alzheimer's or Parkinson's or other disease phenotypes using diffusionmri and a machine learning model. More recently, people have been trying to also create the biomarkers themselves using models using learned features. So brain age is the most famous, perhaps, but any of the RDoC matrix indices could also be a candidate for this type of learned feature, learned biomarker. Of course, machine learning's promise for automating the laborious stuff means that it's been used to do automated segmentation, automated lesion, vessel, hyperintensity. You know, even the most basic brain segmentation is a machine learning application, right? And even more recently than that, we've been seeing image-to-image tasks. So from a diffusion image, trying to predict other image or spatial field valued outputs, right? For us here today, machine learning is going to be equivalent to deep learning. This is not true overall, but for a lot of these tasks, the state of the art is a deep learning, is a deep network. So yeah, that's going to be our purview for today. Right, so on the left-hand side, we have the image. On the right-hand side, we have the label. And a lot of these models are predictive models where we just try and get P of Y given X. So the label likelihood given the input image. This is a notation change from previously because we no longer want to learn about associations, or it's a less pressing matter to learn the associations between labels and images. Instead, we want to optimize for pure predictive accuracy, right? And we still have the scanner context here. We still have scanner variables S confounding our analysis. And we're likely to overfit because many of the popular machine learning methods are very flexible. So we're going to learn the scanner signals. Moreover, or I guess more importantly, we have this concept of test time, which doesn't really exist in the post-hoc regression context, where at test time, we might encounter new scanners and new sites. And so S star here, and those we want to generalize to well, which isn't really a concept in the previous setting. Right. For this tutorial, deep learning is further going to be just abstracted to flexible function approximation. I know that many people have different disagreements and beliefs about deep learning and how to deal with it and how to appropriately think about the theory of it. We're just going to abstract it away to a flexible function approximator. Yeah, it makes it a little easier. So given our flexible function approximators, our deep networks, how do we check for overfit? How do we check that we need to harmonize something? Well, we can create a test set and do this empirically, where we create the residuals from what we're predicting and build a confusion matrix. So build a table. Maybe you could do a statistical test at this point. You don't have to. You could also plot embeddings, so t-SNE or UMAP, and then color them by site and see divergences there. And you could also plot the residuals by site. This is similar to the confusion matrix. All of these methods will likely show you that if you do a naive method and you actually have site-wise variance, that you will fit to it. And because we know in diffusion methods that there really is quite a lot of site-wise variance, if you haven't fit to it using the naive method, then either you really don't have multiple sites, or your method, your data is so noisy that you can't fit to anything, or you need to use a more flexible method. You're under training your method, right? So what to do about that? Well, if we ignore it, then we will be in trouble, because as the test site again comes in, it might bias our results by which scanner is most similar to the test time scanner, which isn't a thing we want to do, because if the test time scanner is a GE scanner and our training data are all different GE or Siemens or Philips scanners, there isn't a reason that the scans on the GE scanner are more similar in diagnosis to the other GE scanners. That doesn't make sense. That's not a causal line we can draw, so we don't want to do that, right? We could try a conditional model. So this would be similar to the random effects or the combat harmonization we talked about previously, where we're conditioning on the scanner effect. But here, once again, we have test time scanners, so we can't condition on something we haven't seen before. But also, we have the notion that we want to take out the scanner effect. We don't actually want to have the result given the scanner effect, or at least not in this simple setup, right? So maybe that's not the correct way to go about things. And I've already spoiled it, but instead, what we could do is take out the scanner signal. So we could learn a representation that's invariant to scanner or site. So this is a Z that's orthogonal to S. And by learning such an invariant representation, we remove the information about S from Z, and then whatever we do with Z will also be similarly S unrelated. And this is a trick that we're taking from domain invariance, and it's also been seen in algorithmic fairness and other machine learning domains. And we're applying it here where S is, instead of being a domain, is a scanner or site, which I guess you could consider as a domain index, right? There are a large number of approaches for this. Adversarial models, disentangled models, variational bounds of various sorts. And we're going to talk about a few of them here. Right, so one example, the adversarial one, which I think is the easiest conceptually. We're saying we have an encoder network, Q, which goes from the input domain, the image X, to representation Z. And then we have a predictor, which goes from Z to our desired label. And we want the predictor and the encoder to do well. So we want to predict Y very well. So that's a primary loss. But then we also have a secondary loss on Z, where we want Q to produce Z's that are uninformed of the site. Right. So that's the invariance constraints, right? And so what does this look like? Little graphic on the right-hand side. We have an encoder, a predictor. Those are both in black, the primary network. And then we will have a constraint on Z. And in this case, it's an adversary. So we're actually having a third network, the adversarial network, that tries to predict S from Z. And if we can do it well, this is actually a bad thing. So we're going to flip around the loss function on the adversary and say, oh, if we can trick that guy, if we can trick our adversarial network, then we're doing well. And this is first introduced in this context in Ganin et al. It's the same conceptual adversary from GANs, so 2014 or earlier. It fits into the adversarial methods purview, right? And it's been used in brain imaging several times. Dinsdale et al. Was the most recent one that I remember at Mackay last year, a brain age use case. But of course, it's older than that. And so at IME in 2017, people used it for segmentation, and I'm sure there are many examples which I'm missing. But since it's conceptually the easiest, I suggest you try this out first. So if you're having site-wise variance problems, adversaries are very easy to implement. They may not be the best overall, but right, you can look at the previous deep network videos in the DIPY Workshop to get some hints on how to do this well. And it is the same adversarial process as GANs, so you can also look at those tutorials. Right. Here, instead of the GANs supervised versus real, we have to have supervision of the site, but usually we know which site each image is from, so that's pretty easy. And a word of warning, if you were to implement this naively, just straight out of the box, Ganin et al. In 2015 and other early methods use the gradient flip trick. So that's a trick on the adversary to train it all at the same time. Do not do this. The gradient flip trick is is suboptimal because you want to overtrain the adversary. You want to have a very well-informed person to fight against, or network to fight against, so that your primary network, the one in black, can do the best. Because if you can trick a foolish adversary, then, well, that's not much to brag about at all, right? But if you can trick the best of all adversaries, then this is a better thing. So you want to tune the critical index, or also known as the amount of times the adversary receives training data versus the amount of times the primary network receives training data. So yeah, these are just some implementation notes. Great. In 2018, I and my co-authors were able to show that adversarial networks and many forms of disentanglement and variational bounds, they all form this one giant class of invariant representation models, which we've been talking about this whole time. And essentially what we're trying to do is force Z to be orthogonal probabilistically to S. So like we want Z to be independent of S. And then by the data processing inequality, we can say that everything downstream of Z is also similarly independent of S. And this is very intuitive, but we put some formal math to it. And so other methods fall out of it. And that means I'm going to take some ego time to present to you our own method, which is a variational bound, so it doesn't have adversaries. Yeah. So we'll go through that quickly so you don't have to endure my methods too long. But I think it might be interesting to look at, and it's also the one with the prettiest pictures that I have access to. So, right, in our method, we're doing image-to-image transfer. So our Y domain actually is another image. In fact, it's the same image domain. It's another diffusion scan, but at a different site. So we want to move images from one site to another using a neural network. And the way we're going to do that is a conditional autoencoder. So our encoder is the same. It's QZ given X, goes to some encoding Z. But we have a conditional decoder now, which not only outputs into the X domain, outputs a diffusion scan instead of a label, but it takes in a site label, so S. And according to our 2018 paper, we can break down this invariance criterion as the mutual information between Z and S, which is a relaxation of our orthogonality constraint. And that we can further break down into a conditional reconstruction and a compressive term. So if we compress Z, and we can do well at conditionally reconstructing Z, so reconstructing X given Z and S, well, intuitively that makes sense that we would remove S from Z, because if we're trying to reconstruct, so build X again, and we hand it back S, then we don't need to have S and Z, right? Like we're handing it S for free, so we can remove it from Z, right? So that's what this bound says. And there's other alternatives as well. Recently, Uma Gupta from USC also published a contrastive divergence version of this, which is using more popular recent technology, and it works very well. So I suggest you look at that as well. Right. So this is for diffusion imaging. This is a 2020 paper, and it takes in a patch in spherical harmonics and outputs a patch in spherical harmonics, which are then mapped to B vectors. And it has an adversary, so you can view this as a VAE GAN if you want to get into the weeds. But really, it's using the same idea. We're compressing away S information at Z and outputting our desired label, which happens to be an image in this case. This whole class of methods is unsupervised. So the adversarial ones as well, they're unsupervised in the sense that we don't have to have examples of the same image at different sites. So that means we can train on just unpaired images that we have. So we know all the sites for the images, but we don't have examples of the same subject. We don't have traveling phantom data. Yeah, we can do that in training. And then at test time, we can choose a target site. So the green one in this case, and map everyone to the green site. Yeah, so this is a property shared by all of this class of methods, not just mine or Umang's or, yeah. Great. And this tends to work pretty well. So this is compared against a scale and shift regression, which is done in a nonlinear registration sense. That's the Mirzalian et al. Papers in 2018 and further. And compared to those, we do quite well. Right, so you can see our methods, two versions of our methods on the right-hand sides of this plot. Right, so this is a whole class of harmonization or domain invariance methods for deep learning. We had adversaries, there are disentanglement methods, some of which appeared at McKay last year as well, and variational bounds, which is our 2018 paper. And these are all in the same class of remove information from Z, right? And so people have used this for segmentation, image to image, and as well as brain age. There are things outside of this class of models. I didn't really get into it because it's a wide field and because they don't really organize well, or they don't coalesce into like one single other class, right? But you can try bootstrapping. You can just resample your data. This is a little harder with neural networks because they're so flexible, but you could try it. You can try augmentation. If you had a forward model of which scanner or which coil did what, then you could use that and you could augment your data and be robust to S through augmentation, right? You can, if you had supervised phantom data, you can design networks for this. And so Nath, Vanderbilt, and yeah, that group built such a network. So this is like a paired network where it knows about ground truth. And you can do tricks like that. It's a little more expensive, but it actually works quite well. And Mirzalian, of course, introduced a scale and shift regression, which was similar to the combat harmonization, at least in formulation, but you can do it for image to image. So that also works. And of course, we have not explored the whole domain of the whole space of solutions here. So there are likely other methods out there that haven't been really introduced yet, maybe in other fields or just not at all. Yeah. This is active research here. Right. So that's the end of harmonization part 2. I know that there was a lot of deep network whirlwind going through as well, but I encourage you to get into it, especially if you're using deep methods and diffusion at the same time. Accounting for the site-wise variance is very important. Otherwise, introducing a new site, well, it's a strong factor. Invariance is one method, but exploring them all is pretty good. Great. Let's talk about part 3, where we're going to step back a bit. These are about open and meta problems in harmonization. So the giant table that I introduced earlier from Alyssa's Yu's paper, and yeah, the issues there. Well, this table is already out of date, right? There's probably more studies been published, but also it doesn't really cover all the diffusion metrics, and we can't accurately describe how each diffusion metric will change given a new site. We don't have the forward model usually. No, at least as to my knowledge, we don't really have a great forward model of how diffusion signal will change at a new magnet. So it would be wonderful to map out that space. I understand that it will be very expensive, and there's little willingness given other projects like disease-based projects. You know, this is a very meta research angle, studying how diffusion research changes by scanner. But it's still important in that we need to understand the dynamics, the operating characteristics of our instrumentation, which in this case are our MRI machines. Right. And one important aspect of this would be getting more phantom data. So more traveling phantoms, more people scanned at multiple sites. Yeah. Another issue in the meta context is that in reviewing especially for clinical journals, we often want very simple stories. This isn't the case all the time, and I am definitely to blame as well as other reviewers for asking that, oh, why are you doing such a complicated statistical model? Are you trying to hide something underneath all this machinery? But we also ask that because we ask that the models be simple, we're paring away at the nuances that we could dig into with more interesting models, more interesting hierarchical models, and or exploring the deep networks themselves. So you're right. I think for reviewers, I think it's important to allow nuance in statistical models. It's not always people trying to hide or boost their p-values, right? And a third problem, and this is mainly for deep networks, is the worst scanner syndrome, which is something that my postdoctoral advisor, Polina Golan, and I have been thinking about for a little bit. And we put it out on arXiv this year. And yeah, so what is it? The worst scanner syndrome is essentially this fact about invariant representation models. They're the easiest to implement, and they're very straightforward in their intuition. But if they actually achieve Z orthogonal to S, so if they actually make our representation invariant, then the amount of predictive power they have is exactly bounded by the worst site, or exactly bounded, is bounded by the worst site, right? So this is okay if we only have two sites and they're relatively similar, biobank to HCP, they're both great scanners. But if we have a large number of sites, the overlap in sites goes down, right? And if we're saying that our Z has to be invariant to site, then we only get the overlap in the signals. Worse yet, if somebody slips in a really bad site, like total noise or zeros everywhere, or MRI of knees instead of brains, the only site invariant Z is a irrelevant Z, is one that is not relevant to Y, because somebody slipped in a scan that's in that doesn't have any Y information. Well, then the best possible Z that's also invariant cannot have any Y information. Otherwise, it would be site invariant. It would be site informative, right? So this is a duality of this invariant representation model, right? So these are some open problems. I'm happy to discuss them. Even though kind of ending on a dour note, I think it's really important to do harmonization, because otherwise we have an unchecked source of variance, and it's one that's very easy to at least document where our scans came from, so we can contend with it in varyingly effective ways. Yeah, hopefully this was helpful. Hopefully you have a whole bunch of new terms to Google, and maybe some new methods to cognate on and apply to your own work. Feel free to email me, and thank you for listening.